Well, this is it, kids. We are starting chapter 12, the last chapter in your textbook, and the topic is limits. And limits is actually not only the last chapter of pre-calc, but it is really the first chapter of calculus. So calculus is not only a lot of concepts, but it's also big on notation. It's almost like learning a new language a little bit. So first things first is how to read this sort of in your head. And this is read as the limit of f of x as x approaches negative 3. That's why x has the arrow, x approaching negative 3. And f of x, the function, means the same thing as y. So what a limit is asking you for is as x approaches negative 3, so as x gets infinitely close to negative 3, what is the value of the function? Or in other words, what is the y value of the function approaching? And that's what all a limit is asking you that. And if the answer, if what that y value is approaching is a number, well, then that number is the answer to this, is the value of this limit. If the answer is not a number, then we would say that the limit does not exist. And that's going to be a common phrase, does not exist, commonly abbreviated as DNE because it's used so frequently. You might even, if you've ever seen the movie Mean Girls, now it's getting a little bit old, but it's still a good movie if you ever see it on, Lindsay Lohan, the big climax of the movie is, the limit does not exist. Poor Lindsay, where did she go? But anyway, we'll talk more about what could make a limit not exist. But here it is in brief, and I don't expect you to absorb all of this right now. But in order for a limit to exist, the left and the right have to be approaching the same value. So if the left and the right do not equal each other, we would say the limit does not exist. If the graph has unbounded behavior, so in other words, if y is approaching not a number, but infinity is not a number, it's sort of a concept, then we would say the limit does not exist because of unbounded behavior. Or if the graph is oscillating between values, sort of think of like a sinusoidal graph that just kind of goes back and forth. It doesn't really approach a particular number and it doesn't go to infinity, it just kind of cycles back and forth. That would be what's considered an oscillating function, and we would say the limit does not exist for a specific part of that, for the end behavior. But the best way is to just maybe see some examples, and so no algebra at all on this, just starting with a graph, a crazy looking piecewise function that has all kinds of different pieces doing things. You'll notice there's a hole in the graph, there's a vertical asymptote. Over here there's a horizontal asymptote on this side of the function. There's a hole, there's a point kind of floating above it. You have this right here, which kind of looks like a parabola or some sort of polynomial. I think the graph got cut off. It should really be kind of going like that. But this has just a lot of little characteristics, and you'll see like a variety of these limit questions as it applies to this. And eventually we make the leap to doing it with no graph, doing it just from the algebra. But that's why it's nice to remember what makes a hole in a graph algebraically, what makes a vertical asymptote, what makes a graph do this sort of discontinuity where it just jumps down and breaks the graph totally. So let's just see these examples here. And you can always pause and rewind on the video, or you can pause it and try it yourself and then see if I get to it and if you got it correct. So whatever you like. So the very first question is the one that I started with. What is the limit of this function as x approaches negative 3? So the first thing I would do if I were looking at this is I would say here is negative 3, the x value, and here is negative 3 on the graph. And as you approach that point from the left and the right, so I'm using my fingers here, as I approach negative 3 from both sides, what is the y value of the function approaching, if anything? And as you get infinitely close to that point, the y values from both sides are approaching 1, the y value at that point. So that's the answer, 1. As you approach -3, the y values or the function approaches a value of 1. That's it. That's that easy. Number 2, f of 1. This is hopefully not anything new. This is just function notation. This is asking you what is the y value at 1. It's nothing about a limit or anything calculus-wise here. So on this graph, when x is 1, the y value is 6. That's all the function is asking you for. What is the limit of the function as x approaches 1? So again, as I approach 1, here's 1. As I approach 1 from both sides, what is the y value approaching? It is approaching that same value of 6. So just the reason I put these side by side is because they frequently might be asking you, although they're technically different questions, it's the same answer. You're talking about what is happening at this function as x approaches 1, and it happens to just be the same value as what the function is at 1. But these two things are not always the same. So, and you'll notice that in some examples as we go further here. What is the limit of this function as x approaches -1? So here's -1 on the x-axis. So on this graph, you can do all kinds of things, but as you approach -1 from the left and from the right, now from the left on this graph, as I approach -1, the y values are approaching 5. As you approach -1 from the right, the y values are approaching 2. They are not approaching the same value. So it's not a single number that we agree on the function is approaching. So this is a case where we say the limit does not exist. And what I'm going to do is, in parentheses, I'm going to say left does not equal right. And that's sort of your way to communicate to me that you know why it does not exist. So for the time being, like this year basically, if you say the limit does not exist, DNE, I want you to give me a reason. Which of the conditions is it? Left doesn't equal right? Is it unbounded behavior? Is it oscillating? Number 5, what is the f of 6? So in other words, when x is 6, what is the y value? And when x is 6, you'll notice there's a hole in the graph here, but there is a point. When x is 6, the y value is 4. So f of 6 is 4. That's the y coordinate of that sort of floating point. But what's the limit as x approaches 6? Now, as you approach 6 from the left and the right, the y values are approaching whatever the y coordinate of this hole is. As I get super close to there, the y values are going to be getting super close to 2. And you see that hopefully illustrates the real difference between these two questions. This is saying what is the y value at that point, and this is saying what are the y values approaching as you get close to that x value. And you see, so they can be the same answer as in 2 and 3, but they might very well be different answers as in number 5 and 6. So hopefully that's a good side-by-side comparison. What is the limit of this function as x approaches 2? So on this graph, as x approaches 2, so here's 2, so think about left and right. As you approach from the right, the y values are approaching 5. As you approach from the left, the y values are also approaching 5. So that's the answer. If they both agree, they're both going to the same value, it's 5. Notice it is irrelevant. There's no floating point here. The function does not even exist at 2. There is no y value. But that's not what a limit's asking for, so that's okay. It's just what is it approaching. Number 8, what is the limit of this function as x approaches 5? So you'll notice 5 here is this vertical asymptote. And as you approach 5 from the left side, this graph is going down, just like anytime you approach a vertical asymptote, it doesn't just stop. It's either going down or up to infinity or negative infinity. In this case, it's going down to negative infinity, and on this side, it's going up to positive infinity. So what we say here is the limit does not exist, and it's because this is the unbounded behavior. You can just write unbounded if you like, and that's whenever you're going to infinity. We're going to say the limit does not exist unbounded. It doesn't really matter whether you're going to positive infinity as you are on the right side or negative infinity as you are on the left. But either way, it's not leveling off and approaching a single number. It's growing in an unbounded fashion. So unbounded. Sometimes people think we should be saying left does not equal right in this scenario. But even if the left and the right were doing the same thing, so like suppose this side was going to positive infinity also, I still wouldn't say the limit exists because they're both going to infinity. That's still unbounded behavior. So it's not really the fact that the left and the right are not doing the same thing. So it's more about the infinity element. And now you'll notice these last two are asking what's the value of this function as x approaches infinity. So now you're talking about as x approaches infinity, which is another way of saying as we go infinitely to the right. That's essentially asking for end behavior. You know, that's actually the small notation we used to use when describing end behavior. We would say as x goes to infinity or as x goes to negative infinity. What's f of x doing? Well, on this graph, as we go towards positive infinity, it looks like the y values are approaching this horizontal asymptote. Whether or not they get there is irrelevant, but I know they're approaching this HA, which has a value of y equals 1. So I would say that is what the function is approaching, 1. And on the left side, as x goes to negative infinity, so the left end behavior basically, as you go to left and left and left, based on what this graph is showing you, it looks like the graph is not leveling off at all. It looks like it's taking off to positive infinity. So there might be times next year where your calculus teacher wants you to say infinity is the answer. But for right now, we're going to say the limit does not exist, because when it comes to limits, we're looking for a number to be the answer. And if it does not, it's DNE. And infinity means that's unbounded growth. So, okay. That's just a basic idea of limits, and that's the main connection I want you to make today, is that visual connection with what a limit is asking for. We'll get into all the algebra of it, of course, but I think a big part of it is understanding what it's asking you for and, you know, trying to visualize what's happening. So if you have any questions, of course, feel free to email me. Have a good day.